It's quite easy for us in our daily lives to imagine the Earth as this stationary object with everything else above our heads moving around us. But of course we know now that that's far from the case. Earth, as all planets do, are constantly doing three things while in orbit around the Sun. Because everything it does is constant, we humans on the Earth's reference still feel as if nothing is happening. The first, quickest, and most noticeable thing is rotation. Here you see the Earth rotating along its axis at 4,000 times speed, or a little over an hour per second. The spinning rate is constant, and you should see a full rotation every 21.6 seconds. However, at the same time, it's also locked by gravity into an orbit around the Sun. Still going by 4,000 times speed, look how little of its orbit it moves through each day. Okay, let's bump this up to 400,000 times. The third motion is a little harder to describe and a little harder to simulate, but it has an effect on how the stars are oriented in the night sky. We'll get to this. Point is, our little blue marble is moving a lot, and in many ways. My name is the number 12, and you're watching Nerd Candy. Now let's not pretend for a second that rotation isn't noticeable. After all, unless you happen to be watching this from the North or South Pole, you know that there is a day and a night. If it's daytime, the sun will be in the sky somewhere. If it's nighttime, instead of just seeing one star in the sky, you see thousands of them, represented by little points of light. Now those stars are still out there during the daytime. You just can't see them if the sun's brightness overpowers them. Speaking of the sun, this is where the common sense portion of the video ends. Let me ask you, how long is a day on Earth? Just think about it. If you said 24 hours, you're correct. But that's not the only right answer. I'm going to use a Celestia space simulator to skip ahead exactly one day. That is, change the date without changing the hours, minutes, or seconds. See if you notice anything. Did you see North America move a little bit to the right? If not, here, let me skip ahead exactly 240 hours. 10 full days, give or take 0 seconds. There are, of course, two explanations for this. One, Celestia is simply defective and this is all a glitch. But would I really be using a product I know to be defective for an educational video? Actually, that is something I totally would do, so please disregard that rhetorical question. But no, it's no glitch. It's exactly the way things are supposed to be. Humans did not divide up a day to 24 hours just because it was easier, and humans were not simply too lazy to fix the system once they figured out that Earth's rotation isn't precisely 24 hours. Remember, while Earth is spinning around its own axis, it also revolves around the sun. That little blip in the rotation, that is because the Earth actually rotates once every 23 hours, 56 minutes, and 4 seconds. We call this the Earth's sidereal rotation. But because Earth revolves at the same time, during a 24-hour period, the Earth completes 1/365th of its orbit. Putting them side by side, you can see that there's very little difference, but it's just enough to be the difference between 23 hours, 56 minutes, and 4 seconds, and 24 hours and 0 seconds. There is a formula for this, and it works for every planet that orbits prograde, that is, the sun rising in the east and setting in the west. Taking the length of the sidereal day and dividing it by 1 minus the length of the sidereal day over the full orbital period gets you the synodic day. In other words, the amount of time between two sunrises. And so, mystery explained. Now, one brief thing that is worth noting is if I advance time by exactly 1 day from the Earth's perspective and look up at the sun, it won't be in quite exactly the same position, but that is because of the axial tilt of the Earth. Because of the tilt of the axis, the sun is not always in the same position every day, and that's what gives rise to the seasons. This process, of course, affects all the planets, but with different degrees of how much it matters. Take Uranus, for instance. Its sidereal rotation is 17 hours, 14 minutes, and 24 seconds. But it orbits so far from the sun that its revolution period is over 84 years. So, if I advance time by 17 hours, 14 minutes, and 24 seconds, which I guess it's already done for me, you probably won't notice anything at all. From this, we can conclude its synodic rotation might as well be the same as a sidereal rotation. Mercury, on the other hand, is quite the subject. With a combination of its very long sidereal day and its very short year, running everything to the formula gets us a synodic day twice as long as the year. Mercury is a special case because it's the only planet tidally locked to the sun in what's called 3-to-2 orbital resonance. That is, it completes 3 rotations every 2 years. You know who else this affects? That's right, planet Earth's favorite natural satellite, and only natural satellite. The moon is to Earth like Mercury is to the sun, tidally locked. However, instead of a 3-to-2 resonance, it's 1-to-1, meaning that it rotates and revolves in such a way that it presents the same hemisphere to Earth at all times. I got the moon rotating at 160,000 times speed. It's a lot slower to rotate than Earth, and it completes a rotation every 27 days, 7 hours, and 43 minutes. To give a better visual on the resonance, let's turn on night lights in Celestia and go back to Earth. If we stare straight at the moon throughout its orbit, nothing changes except for its apparent size from having an elliptical orbit and, of course, the phase. I mentioned the rotation being 27 days, 7 hours, and 34 minutes. So, noting that I placed the Copernicus crater strategically right on the boundary between day and night, let's skip forward precisely that time. And there you go. It's still there. It just rotated into darkness. And you'll soon see why. Went back to the original date. Now watch on the right, the moon's orbit is in red, and the moon itself, of course, is marked for you. I'm going to skip ahead again, precisely 27 days, and 7 hours, and 43 minutes. And the moon is in the exact same spot in its orbit. Let's go back to Earth's perspective, and back again to the first date. Now, instead of paying attention to the moon's orientation, I've turned off ambient light completely so we can focus on the phase. Now, if we advance forward, we get... That's not even close to the same phase. That 27 days, 7 hours, 43 minutes number I keep mentioning is, you guessed it, the sidereal rotation of the moon. The revolution of the moon around Earth is perfectly synced with the sidereal rotation. So, why the different phase? Well, turns out, it's coming from us. And we've been here before. The discrepancy in the phases has to do with Earth moving around the Sun. After all, the Sun will hit both Earth and the Moon at different angles depending on where Earth is in its orbit. The Moon is close enough to Earth that the light from the Sun basically hits them both at the same angle. And while this motion accounted for a 4-minute difference between Earth's sidereal day and its synodic day, the Moon's sidereal day is a much bigger fraction of Earth's orbit. And this is why its synodic day, or in other words, the time between two new moons, is 29 days, 12 hours, and 44 minutes. Now we understand rotation. And now we understand how rotation and revolution are related to each other. Before we move on, though, I want to make a belated point that might have caused confusion. In daily conversation, we use the term revolution in ways that actually describe rotation. For instance, when we talk about a car tire's RPM, the R technically stands for revolutions, and it measures the number of times the tire completely turns 360 degrees over itself per minute. Or in a golf tournament, if someone just barely misses a putt, you'll often hear the commentators describe the ball as being 1 revolution short. What they mean, of course, is a 360-degree rotation. And I've been going by the term rotation this entire video simply because that's what astronomers use. And astronomers are smarter than you. That means you! Identified as Toast? Look at that guy. What a stupid name. What a stupid request for me to play. Actually, who am I kidding? He's my friend and I really like him. I need to shame some random person who's never done anything bad to me who might not be smart. Yeah, heck you, Sheldon Day, defensive tackle for the San Francisco 49ers. I bet he isn't into astronomy. I bet he doesn't even know that he was born exactly 10 years before the Cassini spacecraft entered into orbit around Saturn. Does he? Is he actually smart? I have no idea. Anyway, so we've already looked at revolution quite a bit in conjunction with rotation. Now let's discuss a few aspects of revolution as a standalone thing. First and foremost, Kepler's laws. Kepler's first law is simple. It simply states that all planetary orbits are elliptical, with the Sun being located at one of the two foci. While a perfect circle has a continuous radius and one center, an ellipse, you know what, you guys are smart, I'll just let you study the chart. If you've ever been to some astronomy-related encyclopedia, you've come across the term semi-major axis. While looking at this chart, that term means exactly what it looks like. One half of the major axis of an ellipse. This is considered more or less a planet's average distance from a star. The other critical aspect of a planet's orbit is its eccentricity. This is calculated with the formula A equals alpha divided by the square root of 1 minus epsilon squared. The epsilon is the eccentricity, the A is the semi-major axis, and the alpha, well, take it from me, you do not want to know what alpha is unless you are seriously pursuing a career in physics full-time. I took an upper division physics course about it. I have no idea what any of it means. If you want to look it up, well, good for you, but it's not something that I can explain in a single video like this. In order to make sure this video is still understood by everybody, let's just say alpha is a specific quality that is constant for whichever ellipse you happen to be looking at. As a matter of fact, eccentricity basically defines an ellipse. As you might expect, eccentricity of 0 means a perfect circle. Eccentricity between 0 and 1 gets you an ellipse. Eccentricity of precisely 1 results in a parabola, while anything greater than 1 is called a hyperbola. If an object wants to stay gravitationally bound to another object, it has to orbit in a circle or ellipse. Back to Kepler's laws. The second law states that a planet covers the same area arc of an ellipse during the same amount of time. Intuitively, this makes sense. After all, in a perfect circle, the planet would be moving at the same speed the whole time, so it would cover the same distance per unit time, no matter where it is in its orbit. In the case of an ellipse, what this effectively means is the planet moves faster when it's closer to the sun. So if the red arc of its orbit and the white arc of its orbit were over the same length of time, the area of those arcs should be the same. Now if that sounds a little like gravity to you, well, it should. And it should impress you that Kepler figured this much out before Newton did most of his work. Newton relied heavily on Kepler's second law to draw an analogy between the force of planetary gravity and the force that makes apples fall to the ground. Heck, even Einstein's theory of general relativity, at least on the scale of the solar system, is more or less a reimagining of Kepler's laws of motion. Kepler's third and final law is more mathematically involved. You must be so excited! Really though, there isn't much to it. P squared equals A cubed as long as P equals the orbital period in years, and A equals the semi-major axis in astronomical units. Kepler himself was surprised when he saw how well this relationship worked. He found it curious that something as grand as a solar system could be described as something so simple. Yet even today, after all our technological advances, this relationship holds. Well, it holds as long as we're talking about a planet moving around the sun, because if you change the body at the center, then we're talking about a different mass, different density, and, well, you're going to have to make a few modifications to this. However, the relationship is still there, you just got to mess with the coefficients a little bit. This rule was set up so that the Earth would be the easiest planet with a semi-major axis of 1 AU and therefore a period of 1 year. Now, if there were a planet 4 AU from the Sun on average, then the period would be the square root of 4 cubed, or the square root of 64, which is 8. So a planet 4 AU from the Sun would take 8 years to complete its orbit. How can we find out how fast a planet is moving? Well, if we know the semi-major axis and are given a length of time, we can come up with a good approximation for a planet's average speed. Again, we may as well use Earth as an example. We know that our semi-major axis is 1 AU, which translates to roughly 149.6 gigameters, or 149,600,000 kilometers. And 1 day is roughly 1/355th of our orbit. With that, we have an arc length. In other words, the distance Earth just traveled in that 1 day. arc length here would be the semi-major axis times the angle 1 out of 365 in radians, which is 0.01721. It is worth noting that this is not exact because of the fact that Earth's orbit is an ellipse, but it's close enough to a circle that this average comes out to a reasonable estimate. And that estimate is 2.57 gigameters per day, or 2,570,000 kilometers. If that sounds like a lot, it should. To put it in everyday terms, planet Earth and everything on it, including you, is revolving around the sun at 29.74 kilometers per second. Think about it. Your planet, the ground you're standing on, every single second of every single day, is moving roughly 29,740 meters through space relative to the sun. Of course, it depends on how close it is to the sun. It goes a little bit faster when closer to the sun and a little bit slower when it's further away. But even if you happen to be watching this at a NASCAR race or in a commercial airplane, there is an overwhelming chance you will never ever move faster than your planet as long as you live. Probably not even close. For the Americans in the audience, first of all, get used to the metric system because it makes a whole lot more sense than our stupid system. And second of all, if you really want a nice little vision for how much that is, every 3.7 seconds, the Earth moves the equivalent of 1,000 football fields. You can understand that, right? And remember, these principles of revolution apply to pretty much any natural orbital situation. Whether it's Earth or another planet going around the sun, or a moon going around a planet, just remember to change the coefficients and the principles should hold. If anyone was curious, here are the speeds of all the other planets. But wait, there's one last component of revolution. If you put revolution on a really, really big scale, Kepler's laws finally become completely useless. So, let's zoom out. Way out. There's something happening not just to Earth, but to the sun and everything around it. It is impossible to see the sun as an individual star from this perspective. This Celestia space simulator does not show what's going on because the process takes so long it's hard to want to bother. That, and they'd have to program this for every single star in the program. But the sun, and by extension the entire solar system, really is moving around the center of our galaxy, the Milky Way. Except now, instead of dealing with distances in gigameters, now we've got distances in thousands of light years. The time for one orbit is called the galactic year. No one knows for sure what it is, but the best estimate is 225 million years. For some perspective on that, the dinosaurs became extinct just 29.3% of a galactic year ago. Heck, the entire Mesozoic era, the entire time period dominated by dinosaurs, didn't even last a full galactic year. One galactic year ago, the continents were still huddled together in their Pangea formation. It's a ridiculously long amount of time, and yet, because of how huge that orbit is, the solar system, in order to complete that orbit, is flying through space at nearly 230 kilometers per second. Remember when I was trying to make this look crazy fast? Well, multiply that by about 7.5 and now you've really got fast. Remember, that's you. You are, at this moment, moving through the cosmos at that speed. As for what I said earlier about Kepler's laws no longer working, on the galactic scale, something interferes. Now, we've taken measurements of other stars' orbital speeds, and we've managed to plot them on a chart. Here it is. Now, galaxies have uneven mass distribution, and stars are more concentrated in the center, which explains the low velocity of the closest stars to the center. That, and the fact that the mass outside of where you are in the galaxy is pulling you in the opposite direction as the mass inside of where you are. But the kicker is that once you get to around 10,000 light years from the center, the speed of a star stays pretty much constant for the entire rest of the galaxy. In Kepler's laws, the most distant worlds revolve the slowest. Not here. This is different. Not even Einstein's general relativity could account for this. That is, unless you factor in an entirely new source of mass. Dark matter. Wait. Dark matter. I can't really go into detail about it, mostly because nobody knows what dark matter actually is, or at least what it's made of. What we do know is that there's a ton of it. In fact, it outnumbers regular matter, in other words, the entire universe that we actually see and understand, by nearly an 11-to-2 ratio. Its existence helps plug up holes in general relativity, and it explains why revolution kind of breaks down at the galactic level. And that's everything you need to know about revolution. As for the third aspect of Earth's motion, it's incredibly subtle. This shot of Earth shows two sets of axes. You can see the z-axis pointing straight up from our North Pole and the x-axis parallel to the equator, and then you have the frame axis, as Celestia likes to call it, which extends from the magnetic North Pole. As I'm sure everyone already knows, Earth's rotation axis is tilted a little over 23 degrees relative to the geographic pole, but do you know what else this thing does? This axis traces itself around the Arctic Circle. Turns out, plot twist, Celestia does track this, but we have to speed up time 20 billion times to see it happen. I'll give you some time to watch it. What you just witnessed was 25,772 years of axis precession. Earth's axis behaves like a spinning top or a gyroscope or even a drawing compass, making a complete circle around the Arctic and Antarctic in that time. You may wonder how we know this? Well, it has to do with the stars we see in the night sky. Now, I know that I just mentioned how fast we're all flying through the galaxy, and yes, that'll change the way the constellations look. But for one precessional period, it doesn't change too much, especially the stars closest to us. This is Polaris. We call it the North Star, because if you were to stand on Earth's North Pole, it would always be directly overhead. Also, if you ever tiptoe south of the equator, you'll never see it at all. But this won't be the case forever. As our axis draws its little circle around the Arctic and Antarctic, so too does the location of the North Celestial Pole. This diagram shows you a couple of future North Stars, Deneb and Vega, both far brighter in apparent magnitude than Polaris. And then there will be a few millennia without any bright North Star. That's not very noticeable over one human lifetime, but hey, humans have been making star charts for a really, really long time. Everyone knows about ancient Greece. In fact, it was Hipparchus who first suggested that precession exists. They had the run of science for about 7 centuries or so around the birth of Christ, and then when the classical Greco-Roman period fizzled out, the Muslim scholars carried on astronomy for most of the Middle Ages, and then when they had lost most of their interest, that's when people like Copernicus and Galileo had come up. Basically, what I'm trying to say is, we're gonna notice it eventually. Where does it come from? Take a look at our lovely planet. See that shape? That's right! It's an oblate spheroid. It's not a huge bulge, but it's enough to cause gravity anomalies. For a perfect sphere planet, there is no precession. Without going too deep into the physics details, what happens is the pull of the sun and the moon kind of stretches the bulge a little because a small fraction of Earth's mass is a tiny bit closer to them than they would have been at equilibrium. In other words, they pull harder on one half of Earth than the other. This causes torque on the planet itself, and the net result is that the axis twists along its own 23-degree angle with the pole. This was figured out by none other than Sir Isaac Newton, pretty much the GOAT, and he was even able to make a derivation of his own formula of universal gravitation to calculate the total precession force. Let's see what it looks like. No. And with that, that's pretty much everything you need to know about all the ways that the Earth moves: rotation, revolution, and precession. That's how our planet moves. It's doing that every single second, every single day, whether you want to acknowledge it or not. It's a pretty darn cool planet. And, you know, all the other planets do all that stuff too, just at varying degrees of intensity. And it should be noted that, like, I meant to release this video like a year ago. I had like 75% of it done and then just completely forgot that it existed for months and months and months. So, yeah, but hey, I'm releasing it now. Hey, in the comments below, can you tell me how many shirts that I wore during this video, if you could tell? Actually, don't do that. Comment something actually meaningful if you have anything meaningful to say, because that'd be a lot more fun to look at. Anyway, welcome to the end of the video. Thank you so much for watching, and maybe I'll stick to a smaller topic next time, or at least one that doesn't require such a long video. Bye. This process, of course, affects all of the planets, but with different degrees of how much it matters. Take Uranus, for instance. Its sidereal rotation is 17 hours, 14 minutes, and 24 seconds. But it orbits so far from the sun that it's wait, oh crap, I need to have it marked. Can't even see it from here, heck. You know who else this affects? Oh man, I picked the wrong map. Dang it, I picked the wrong map! If we stare straight at the moon throughout its orbit, nothing changes except for its apparent size, and that's just because it has an elliptical orbit. I have it on reverse, don't I? I have it on freaking reverse. Why does recording make my face cam fart?
The other critical aspect of a planet's orbit is its eccentricity. This is calculated with the formula... Oh wait, this is the wrong one. Whoops, bad graphic. As a matter of fact, eccentricity basically defines an ellipse. As you might expect, As for what I said earlier about Kepler's laws no longer working, on the galactic scale, something interferes. Now, we've taken measurements of other stars' orbital speeds, and we've managed to plot them on a chart. Here it is. Heck me, of course the freaking picture gets in the way.